All right, so we are looking at our exam review. Never recorded live before. All righty, so here we go. We're going back to look at limits. So we're going to evaluate the limit of the graph. These are all most of these are two-sided limits. So the limit as x goes to 0. Remember, that's the location of the y value when we get closer to the x value. So at x equals 0, that point does exist. The left-hand limit and the right-hand limit both go to the same value. So that is 0. I'm recording, right? Yep. All righty. No, I want to make sure. I am. All right, so here we go. Letter B, the limit as x goes to 2. So if we look at 2, we're looking at this place here. Note the function doesn't exist at x equals 2, but that doesn't matter. We want the left-hand side limit and the right-hand side limit to be the same. They are 1. We want to look then at the right-hand limit as x approaches 1 from the right of f of x. So we want 1. So here's our 1 as we go from the right. We're approaching the value of 1. Letter D, the graph is discontinuous for what value of x. Remember, discontinuous is where you have to pick up your pencil and set it down somewhere else. That would be at 1 and 2. Questions on number 1. Number 2, then, evaluate the limits. There's a bunch of tricks that we developed to evaluate limits. We're going to look at those as we go through here. The first trick is to just algebraically simplify. Remember, we're going to include the limit until we plug in the number. So this is the limit as x goes to 0. 4 minus x quantity squared gives us 16 minus 8x plus x squared minus 16 all over x. That means the 16s will cancel. That leaves us with the limit as x goes to 0 of negative 8x plus x squared over x. Now we can divide the x to get the limit as x goes to 0 of negative 8 plus x. Now we can plug in the number. So now we're dropping the limit. This then is negative 8 plus 0, which is negative 8. Letter B, another trick we can use is to factor. So we can factor the numerator. This is the limit as x goes to 0. Signs are different. Multiplies to give x squared is x and x. Multiplies to give negative 6, subtracts to give plus 1, has to be a plus 3 minus 2 over an x minus 2. X minus 2's cancel. Therefore, we have the limit as x goes to 0 of x plus 3. Yes.
No, the limit
as x goes to
2. That's plus 3. Is 2 plus 3, which is 5. Letter C, we don't need to do anything. We can just actually evaluate this one. So this is 2 times 5 squared minus 4 times 5 plus 7. We'll plug that in our calculator. That is 37. Letter D, again, we can use our trick of simplifying. This is the limit as x goes to 2. This will factor a difference of 2 squares. X plus 2 times x minus 2 all over x minus 2. X minus 2's cancel, which is why it's undefined. We actually plug in the 2. That's why you get the 0 on the denominator, because those 2 canceled out. And we get then the limit as x goes to 2 of x plus 2. Now we can evaluate, which is 2 plus 2, which is 4. Now we break into trig functions. This is the limit as x goes to 0 of sine of 2x. For that, we're going to need a trig identity. And for that, you're going to look on your pink sheet. And that identity is this. The limit as x goes to 0 of sine of 2x is 2 sine of x cosine of x all over x. That one we're going to break up. The limit as x goes to 0. And we're going to remember we have a special limit for sine of x over 2. So sine of x over x times 2 cosine x. And we're gonna remember that the limit of sine x over x goes to 1. So this thing goes to 1. So this is 1 times 2 times the cosine of 0. Cosine of 0 is 1. So 1 times 2 is 2. We can also evaluate as we go to infinity, find the limit as we go to infinity. For this, we're going to break this up into polynomials. So this is the limit as x goes to infinity of 3x over x minus sine of x over x. What's going to happen? Well, the x's cancel. That leaves us with a 3. And then we're going to recognize that sine is always between 0 and 1. But as x gets really, really, really big, what does this fraction do? Goes to 0. So this is 3, well, minus 0, which is 3. Letter G, we'll use our polynomial trick, splitting this up. So this is the limit as x goes to infinity of negative 2x to the 4th over x to the 4th plus 6x cubed over x to the 4th minus 4x squared over x to the 4th minus 2x over x to the 4th plus 7 over x to the 4th. If the degree of the denominator is greater than the degree of the numerator, it has to go to 0. So all of these go to 0. Here the x to the 4th cancel. We're left with negative 2. Number 3, use the definition of the derivative to find dy dx for y equals 3x squared minus 7x. That is the formula, the limit as x goes to 0 of f of x plus h minus f of x all over h. H goes to 0. That is then the limit as h goes to 0 of the function with the h plugged in. So that's going to be a 3 times x plus h quantity squared minus a 7 times x plus h. Then we're going to subtract the original function, which is going to flip the sign. So minus 3x squared plus 7x. Watch that second sign change all over h. Now we want to simplify that out. That's going to be the limit as h goes to 0. I'm going to skip some steps here. Let me know if you need me to go back and clarify. X plus h squared, we're going to FOIL. X times x is x squared times 3 is 3x squared. X times h, there's 2 of them, so that's 2xh times the 3 is plus 6xh. Same thing for h times h is h squared times 3 is 3h squared minus 7x minus 7h minus 3x squared plus 7x all over h. If we did that correctly, everything without an h should do what? Cancel. So there's a 3x squared minus a 3x squared. Here is a minus 7x and a plus 7x. Now we can divide the h's. So this is the limit as h goes to 0. H will now divide everything that's left, which leaves us with a 6x plus 3h minus 7h. Thank you. Now we can plug in the 0. And that is a 6x plus 3 times 0, which goes to 0 minus 7. That leaves us with a 6x minus 7. All right. And what's the easy way to check that? All right, that's the first derivative. So 2 times 3 is 6. There's our 6x. First derivative, there's the minus 7. Yes.
Well, we need to know that, because normally we get like.
You need to know that equation. Yeah. Questions for Sage? Name 4 places a derivative would fail to exist, not discontinuous, where it fails to exist, and that is on corner, cusp, vertical asymptote, and discontinuity. There are 4 discontinuities, but that's not the same as the 4 places the derivative doesn't exist. Now we're into finding derivatives. And for this, you're going to reference your note card. So for the derivative of the natural log, we're going to remember that d dx of ln of u is 1 over u times du dx. Don't forget the chain rule stuff. That's all the stuff we spent the last month looking at undoing with our integration rules. So this is our u then is x squared plus 5x. I'm not going to show that substitution, but that's basically what we're doing. So that's 1 over x squared plus 5x times the derivative of the inside, which is 2x plus 5. That gives us the polynomial 2x plus 5 over x squared plus 5x. The derivative of 17 to the x, again, we have a formula for that. So d dx of a to the u is a to the u ln of a du dx. Does that look right? So,
Whenever you do that, are you multiplying like ln of a times d, the derivative of u?
yes.
Okay.
We're gonna have the same exponential function, which is 17 to the x, times the natural log of the base, which is ln of 17, times the derivative of u. Well, the derivative of x is just 1, so we're done. Letter C, derivative of a logarithm works actually the same as b. Well, it doesn't. For e to the x, that's e to the x times du dx. So that's e to the 3x. The derivative of 3x is 3. So we have 3 e to the 3x. The derivative of cosine is negative sign, so the negatives have to cancel. The 4 is just a constant, it stays there. We have 4 sine of x. Letter D. On this one, you do have to use the quotient rule. What is the quotient rule? High below, all over the square of what's below. Alrighty, so what is the low? The low is the x minus 1. So we have x minus 1 times the derivative of the high. And is there any way we can make that easier for the derivative of the high? Yes, because we can do well with this. We can FOIL that out. So x times x is x squared. We'll get a 2x plus a 4x, which is a 6x plus an 8. So the derivative of the high then would be a 2x plus 6. The 8 goes to 0. Minus the high. Well, the high is going to be that whole polynomial, x squared plus 6x plus 8 times the derivative of the low. Well, the derivative of x is 1. The derivative of -1 is 0. So that's times 1, which is just what it is, all over the square of what's below, which is x minus 1 squared. And for our purposes, you don't have to simplify that. I just need to know that you know the quotient rule. Questions? Sorry, what?
You want us to include dx at the end?
I don't know what you're talking about. I know what dx is. When we take a first derivative, we've never included the dx. Doing partial, when we do partial derivatives, when we do that's for differentials. We're not doing differentials yet. We're just doing first derivatives. The dx is right there.
Okay, great. Okay, that makes sense. Do you want that?
No.
Here's why I have dy equals all of that in parentheses times dx.
Right, but you're gonna divide the dx. That's the first derivative. That's what I explained that one day
Yeah.
when you came back. Yeah. So really, we do a differential all the time. We always divide it out to be the dx on the other side.
All of the difference.
Yes, don't do that on the final. Thank you. Letter E, derivative of secant is, so that is tangent, but what is x? X is the argument. So we have a tangent of 3x squared times the secant of 3x squared. But we're not done because we have to multiply by the derivative of the argument, which is 6x. If you want to make that prettier, put the 6x in front. Tangent 3x squared, secant 3x squared. That's equal to dy over dx. Number 5, log, we have a formula for that, and that is log base a of u. The derivative then is 1 over u ln of a du dx. U is the 5x, so we have 1 over 5x times the natural log of the base. The base is 2, so this is ln of 2 times du dx. 5x is the u, the derivative of 5x is 5. Can we simplify anything? 5, that's 1 over x ln of 2. Letter G, here we have to use the chain rule if there's something inside. Product rule, this is product multiplying x times sine. We're doing first times the derivative of the second plus the second times the derivative of the first. The first is x, dy dx, is equal to x times derivative of sine is cosine of x, plus the second, which is times the derivative of first, which is just 1. Now, this would be really cruel and you wouldn't actually want to do this, but you could check all these answers by doing what? Integrating back to find the original, but I would understand if you want to do that. Use implicit differentiation to find dy dx. Here we have to use what, Sarah? The differentials for differential implicit differentiation. So here we go. So for this equation, dy dx. Nope. So we're gonna take d dx of this whole thing. X cubed plus 4xy minus y to the 4th equals 7.
B1 and B3 are released to lunch.
The derivative of x cubed is? We're using implicit, so we're different. So we're using, I'm sorry, we're not using differentials. We're just doing implicit differentiation, which means we're still differentiating by x. So what's the derivative of x cubed? 3x squared. The derivative of 4xy, we have to recognize that is product rule. So that's the first times the derivative of the second. So that's 4x times, what's the derivative of y with respect to x? Well, the derivative of y is 1, but since we're differentiating with respect to x, we have to leave a dy, not, yes, dy dx. Good job. Plus, now we have to come back and do the second part, y times the derivative of 4x, which is, so that is 4y, minus the derivative of y to the 4th is 4y cubed. Because we took a differential of a y, we have to leave a dy dx, equals derivative of 7 is 0. We're going to run out of room. Now we want to solve for the dy dx's. We're going to move everything else to the other side. That leaves us with the 4x dy dx minus a 4y cubed dy dx equals a negative 3x squared minus 4y. Now we're going to factor out the dy dx's. So dy dx, we factored out, leaves us with the 4x minus 4y cubed is equal to a negative 3x squared minus 4y. We're going to divide that back over. Therefore, dy
B2
dx
is release to lunch.
is negative 3x squared minus 4y all over 4x minus 4y cubed. Questions?
Why did I do that?
I can't answer that.
So I canceled a 4y.
Okay.
So negative 3x minus 4 over 4x minus 4y. That's not how that works.
Questions? We ready for the next page? Find the instantaneous rate of change for this function. Instantaneous rate of change is the first derivative. We're going to remember that the square root of 3x is really 3x to the 1/2 power. And so to take that derivative, we're going to subtract 1. So that becomes now 3x to the negative 1/2. And we have to take the derivative of the inside. The derivative of 3x is 3 plus the derivative of 2x is 2 minus 3 goes to 0. Now we just want to clean that up and simplify. This is 1 over 3x to the 1/2 power times 3 plus 2. And then we remember 1/2 is just the,
Yeah, you need to bring the 1/2.
I forgot to bring the 1/2 down. 1/2. 1/2. Remember that the square root is, sorry, 1/2 is the square root. So 1 over 2, there's our 1/2. Square root 3x times 3 goes to the numerator plus 2. Questions? Application questions. The farmer wants to design a rectangular pig pen using 110 feet of fence. One side will use an existing wall as a boundary. Find the dimensions of the pen that maximizes the enclosed area. Because we want to maximize, that means we want to find a maximum. To do that, we're going to use a first derivative. First thing we want to do is draw a picture. So here's our wall. So for our fence, we'll draw a rectangle. And I'm going to call this, for lack of anything else, X, Y, and Y. You're free to use whatever you want. We need a formula. We're going to maximize area. So area is equal to X times Y. We don't want to use two variables. We want to use one variable. To get rid of a variable, we're going to use perimeter. And the perimeter of our fencing is, or the length of our fencing is, right, is 110, and that equals the 2y plus x. Good. Now you need to pick which variable you want to get rid of. Because x doesn't have a coefficient, I'm going to solve for x. So x is equal to 110 minus 2y. I'm going to plug that in. So a is now 110 minus 2y times y, and that is 110y minus 2y squared. Now I'm going to maximize. To maximize, we're going to take the derivative of area with respect to y. So I want dA dy. The derivative of 110y is 110. The derivative of 2y squared is negative 4y, and we're going to set that equal to 0, y0, because that's where the first derivative has a max or min. Good job. We're going to subtract the 110, divide by 4, and y is 27.5 feet. We can do a couple of different things to solve back. You either use the perimeter problem or the area problem. Check that, we don't know area. So we have to go back to the perimeter problem to find x, and that would be 55 feet. Questions?
If it says like max or minimize, like it's, you do the same thing, right?
Yes.
Either way, like.
Yes. Yeah. I mean, you have to, it might be a different problem setting up the problem, but you have to figure out the equation you're using to maximize. And then if you need to eliminate a variable, you need to use some other equation to eliminate a variable, and then take the first derivative, set it equal to 0, and so on. Moving on, related rates. First, we want to fill in the chart with answers for the following questions. Alrighty, so we're gonna actually look at A first. That's 10-foot ladder is against a wall. So here is our 10-foot ladder. If the bottom is pushed at a constant rate of 1.5 feet per second. So it can't go in, it's gotta be going out. So it's going out at 1.5 feet per second. How fast is the top of the ladder sliding when it reaches 5 foot, 3 foot, and 1 foot on the wall? That's going to be our dy dt. So we're going to call this x, this is y. So we're going to find the rate that the y is changing up here. To do that, first we're going to use our values of y. So if, first off, we're going to recognize this is a right triangle, that's Pythagorean theorem. X squared plus y squared is equal to 10 squared. We want to find the x values when the y values are listed. So we're going to solve for x. So x is equal to 100 minus y squared and then square root. So if we plug in 5, we get 100 minus 5 squared square rooted is 5 root 3. If you want to use the decimal, that's fine too. We'll plug in y is 3. That's 100 minus 9 square root. And that's square root of 91. Again, you can use the decimal. We'll plug in 1. So that's 100 minus 1. That's the square root of 99, which simplifies to 3 root 11. So those are x values. Now we want to find the dy dt. Also note dx dt was a positive 1.5 feet per second. Positive means we have to be going to the right. Now we need a equation to differentiate. Which equation are we going to differentiate? And we're going to differentiate it with respect to t, in respect to time. So we're going to take the derivative of x squared plus y squared equals 100. And here's where we're going to use our implicit differentiation. We're taking a derivative with respect to t. Derivative of x squared is 2x, but there is no t, so we have to leave a dx dt. Plus the derivative of y squared is 2y, but we're differentiating with respect to t. That has to leave a dy dt is equal to derivative of 100 is 0. We want to solve for dy dt. And so we're going to subtract the other one over. So 2y dy dt is equal to negative 2x dx dt. Well, we know dx dt, that was 1.5. We're going to divide by 2y. So 2y dt is equal to negative 2x divided by 2y times 1.5. Well, what happens to the 2's? And so we get 1.5 x over y. If you want to simplify that, that would be negative 3x over 2y. So there's our formula to find the slope dy dt. For that, we're just going to plug in numbers. And so for our first box, we want negative 3 times 5 root 3 divided by 2 times 5. And that should get you a negative 2.60 feet per second. And for the next one, we're going to use 3 in the root 91. So negative 3 times root 91 divided by 2 times 3 root 11. Whoops, change numbers. Divided by 2 times 3. And that should be negative 4.77 feet per second. And then negative 3 times 3 root 11 divided by 2 times 1. That should be a negative 14.92 feet per second. Why are all those negative? Ladder's going down, right? Top of the ladder is going kaboom. Next is we want to find the rate the area is changing. So to do that, we need a formula for area. What's the area of that triangle? which in this case is x and y. So now we're taking, again, the derivative with respect to time, that is dA dt, so that's our second column, is equal to, here we have to use again the product rule. So the first times derivative of the second, so 1/2 x times the derivative of y. Derivative of y is 1, so that's 1/2 x dy dt, plus the second y times the derivative of 1/2 x, and that is 1/2 y dx dt. Well, we already have dy. We know what dx is. That is 1.5. So this is 1/2 x times the value of dy dt plugged in, plus 1/2 times, this is 1.5, half of 1.5 is 0.75 y. So now we're going to plug those numbers in for dA dt. So working across, 1/2 of x is 1/2 5√3 times dy dt, that was the negative 2.60, plus 0.75 times 5, that gets us a number that is negative 6.5 feet squared per second. Because now we're looking at how area is changing. Same thing for second one. So we have 1/2 of root 91 times negative 4.77 plus 0.75 times 3. And that should get you a negative 20.5 feet squared per second. And then the same thing for the third one, 1/2 times 3√11 times negative 14.92 plus 0.75 times 1. And that is, what'd you get for that one? Now remember, this isn't the total area. This is how fast what is happening. How fast the area is changing. So the area keeps changing what? Faster and faster. Why is the area changing faster and faster? Because
The area underneath lies smaller and smaller, right?
I mean, that's true, but because dy is getting what?
Smaller.
Faster and faster as it gets closer to the x-axis. So the area is also going to change faster and faster. Last thing we're going to look at is d theta. And for that,
Area doesn't have to be absolute value.
no, it's how fast it's changing. Yeah, how fast it's changing.
Speed is absolute.
Speed is absolute value, yes. Velocity is not. See at what rate is the angle the ladder makes with the ground changing? Need you to check me on this one because I think nope, I think I'm good. So what rate is the angle changing? So how do we get an angle out of this? Here's our angle theta. Well, theta is, y is opposite, x is adjacent, opposite adjacent is tangent of theta is equal to y over x. We want to solve that for theta. How can we solve that for theta? Well, that would give us then theta is equal to tangent inverse y over x. So we want to take the derivative with respect to time of that. That gives us d theta over dt. Now here we have to dip into our bag of tricks for derivative of inverse tangent. What is the derivative of inverse tangent? 1 over 1 plus theta squared. So that is 1 over 1 plus y squared over x squared times, now we need the derivative of theta. Well, that's going to be the quotient rule. So now we're back to low d high. So low times derivative of the high is x times dy dx minus the high y times the derivative of the low dx. That would be dt, sorry, dt. All over the square of what's below, which is x squared. And I'm not going to simplify that. You're just going to plug all that into your calculator. So for our first one, lots of inputs here. So we have 1 over 1 plus our y squared is 5 squared divided by 5 root 3 squared times x, 5 root 3, times dy dt, which is this value, negative 2.60, minus the y value, again, 5 times dx, that was 1.5, all over x squared, 5 root 3 squared. When you plug all that in, I got negative 0.3, and this would be radians per second. You might verify that. We'll do the same thing for the next two. I'm just going to plug these in and let you check them. This is negative 0.5 radians per second and negative 1.5 radians per second. How do you verify those? Thank you. So the area is increasing faster and faster, or the area at which the radius is getting faster. Notice, is the area getting bigger or smaller? Why smaller? What's going down? Right, the value is negative, so it's getting smaller and smaller. That's the negative, almost like it's a vector. Same thing here. The angle's getting smaller, faster and faster because it's a negative. Questions that page? We're going to try to make it through 13. And 14. Find the lines that are A, tangent, and B, normal to the curve there. We need our slope, right? We're still using y equals mx plus b here. Sorry, we're using y minus y1 equals mx minus x1. For that, we need a slope. The slope is just the first derivative. That is 3x squared minus 4. We want that at x equals 2. So y prime of 2 then is 3 times 2 squared minus 4, which is 4 times 3 is 12, minus 4 is 8. So there's our slope of 8. We're using the point 2, and we're going to plug that in to find the y value. 8 minus 8 is 0, plus 5 is 5. So we want the line that's tangent. We'll have a slope of 8 at the order pair 2, 5. That's y minus 5 is equal to our slope, 8, x minus 2. So point slope form. That's y minus 5 is equal to 8x minus 16. Therefore, y equals 8x minus 11. How do we get the normal line? The normal line has a slope that is, which is negative 1/8. We're going to repeat that process. Y equals negative 5. Sorry. Y minus 5 equals negative 1/8 times x minus 2. That's y minus 5 equals negative 1/8 x plus 1/4. We'll add the 5 back, and that gives us y equals negative 1/8 x plus 5 and a 4th. Questions? And then your favorite, the graphs of derivatives. Using the derivative, find the interval in which the function is decreasing. Show all your work. The function first, let's go with the function is increasing, where what happens? Function is increasing where the first derivative is positive. It's decreasing where first derivative is negative. So what do we need to find? Well, we need to find the first derivative. So 1/3 x cubed, 3 times 1/3 is 1. That leaves us with an x squared. Minus a 6x plus an 8. We want to see then where those points change from increasing to decreasing. To do that, we're going to set this equal to 0 equals x squared minus 6x plus 8. Looky there, it'll factor, signs are same, both minus. multiplies to give 8, adds to give -6 is -4 and -2. Therefore, we change signs at 4 and 2. Again, to do that, I'm going to look at a table of values. So here's 2, 3, 4, 5, and 1. So again, there's a couple ways you can do this. One is to actually just see what the value is. So we know something, we're changing a 2, we're changing a 4. So if I plug 1 into my slope formula, I get a 1 minus 6 is a -5 plus 8 is a 3. Well, 3 is positive. If I look at a 3 and plug 3 in, that's 9 minus 18, which is -9 plus 8 is -1, which is negative. And if I plug in a 5, I get a 25 minus 30 is -5 plus 8 is 3, which is positive. So where are we negative? We're negative between 2 and 4.
So if it was like the other way, like if the 3 was negative and 1 was positive and 3 was negative, it'd be.
Negative infinity to union 4 infinity. Use the derivative, find the interval on which the function is concave upward. For concavity, we're looking at second derivative. So concave up is where f double prime is positive. Concave down is where f double prime is negative. Well, we already have the first derivative. What's the second derivative? -6. So we want to see where that changes. That's at 0 equals 2x minus 6. Add 6 divided by 2 changes at 3. So again, I just want to use some test values. So we'll look at 4 and 2 in the second derivative. So 4 times 2 is 8. 8 minus 6 is 2. That is positive. If I plug in 2, I get 2 times 2 is 4. Minus 6 is -2. That is negative. Therefore, where are we concave up? Good. Where are we concave down? Good job. Therefore, what happened at 3? Point of inflection separates concavity. Good job. That takes us to 13. Sketch a complete graph of the function. Confirm analytically the points of inflection. Local minimum. Local maximum and minimum points, increasing and decreasing in the intervals where the function is concave up or concave down. All right, so we're going to run through everything. So what can we help? How can we make this a little bit easier on us first? Let's factor this, take out an x cubed. That leaves us with a 6x minus 5. So the first thing we want to find are the x-intercepts. To do that, we're going to set this equal to 0. Equals x cubed times 6x minus 5. That gives us x equals 0 and 6x minus 5 equals 0. Therefore, x equals 0 and x equals 5/6. So here's my sketch. So there's x is 0, there's 1, so there's like a 5/6 right there. Now I want the first derivative. First derivative would be 24 x cubed minus 15x squared. Now I want to set that equal to 0. Again, I can use a trick of factoring to make this easier. We can factor out a 3x squared. That leaves us with an 8x minus 5. Therefore, x is equal to 0, or x is equal to 5/8. And that was, what does the first derivative find? That finds our maxes and mins. So these have to be maxes and mins. To figure out if they are or max and min, we can plug back into the first derivative to figure out what they are. We can also look at the sign changes to see what they are. But if we plug in let's look at sign changes. So we are between 0 and 5/8. If we look to the left of 0, pick a number and plug it in, you're going to get a negative. If you pick a number between 0 and 5/8, for example, 1/2 would be an easy number, plug it in, you're going to get a negative. And between to the right of 5/8, we're going to get a positive. So that was our first derivative. While we're here, let's go ahead and do the second derivative. So f double prime of x is the second derivative. So that's going to be we can do that. Yep, 72x squared minus 30x. We can use a trick here. We can factor out a. Is this a 12? Let's factor out a 6. So this is a 6x. That leaves us with a 12x minus 5. And therefore, x is 0 or 5/12. Now we want to do a check for concavity with 0 and 5/12. To the left of 0, when you pick a number and plug it in, you're going to get a positive. Between 0 and 5/12, you use 1/12 or 1/4, those would work. You get a negative. To the right of 5/12, plug in a half, 1, you'll get a positive.
lunch report back to third hour.
And so now we can come back and answer our questions. And I didn't plot any of this, so let's work through this as we go. What are the maximum points? Well, we need to sketch some of this stuff. So we know that what happened at 0, 0. The second derivative is 0. Second derivative also gets us points of inflection. So 0, 0 has got to be a point of inflection. We also know we have to have a max and min at first derivative is 0. Well, the first derivative is 0. We already know that's a point of inflection. So that means our max and min had to occur at 5/8. So here's 5/8. This was 5/6. So there has to be a maximum in there. We know this is a positive function. It's positive even. So it's got to be going up and up. So it'd be our point of inflection. We have to cut it. And we know to the left of 0 is concave up. So this has to be concave up. Then we got to flip to concave down. That gives us our point of inflection. Then we also have at 5/12 another point of inflection. So that's our concave down right there. Now we flip back to concave up to get our minimum. And then from there, we're just back up all the way. So let's plug in. What's our maximum points? There are none. Our minimum points occurred at x equals 5/8. You don't need to find the y values. Where are we increasing? We're increasing where the first derivative is 0, and that was 5/8 to infinity from right here. Decreasing intervals, that's from negative infinity to 0, union 0 to negative 5/8. Sorry, 5/8. We are concave up where the first derivative is 0, and that is, sorry, concave up where the second derivative is equal to 0. And 5/12 to infinity. We're concave down between 0 and 5/12. And then the only point of inflection was at 0, 0. No, there's a second point of inflection at 5/12, wasn't there? Whatever that y value is. Questions?
Do you want us to put only the, like?
You can just put the x values. Questions? we're gonna pause there. I think we just have 3 pages left. And the exam is gonna work the same way. The second derivative stuff or the derivative stuff will actually be on the second day. So there will be some derivative stuff on the second day test. And then we'll go through integration. And we'll do that tomorrow. That will wrap us up.
So you said like the test will be about.
Have a good day, Maroons.
The test will